So our next presentation was born out of a breakfast meeting. Every couple of weeks, every month, I live in League City, and so we have a breakfast meeting with our team from Johnson Space Center, and they kind of help put things together from the NASA side. Couldn't do it without them. So this year we had a new addition to our breakfast club. His name is Denny Holt, and he had some excellent suggestions on a presentation. And so we said absolutely, of how space technology, once again, looking into the other guy's toolkit, can be translated from aerospace to medicine. So Denny's going to come up and introduce our next speaker.
Thanks, Steve. Well, I've been in this business for about 50 years. I think Dean and I are probably the two most senior Apollo representatives, at least here. And it's been a real treat. And I have to tell you that I can remember when this building was the bakery. and there wasn't much else here except St. Dominic's across the street. And so it's a real treat to see what you've put together and what you built. And I'm blown away, honestly, by the symposium. It is as good as I've ever been to. And I've been to too many of them. I'm representing the McDonald Detweiler Associates, which is the other MDA, for those of you who are not familiar with them. Small outfit from Toronto, Brampton, outside in Ontario. But they're also part of MDA and SSL, or about a $2.1 billion a year operation, and launch most of the commercial satellites out to geosync. So it's a huge company. And they built the Shuttle arm, the Canada arm, the Dexter robot that's operating on the space station. And so Tim Fielding is going to come talk to you about how that morphs into other applications, and specifically medical. And Tim is the product development manager for medical robotics and automation for the corporation. And so how space robotics comes from his toolbox to yours.
Thanks, Amy. All right, thank you for having me here. Yeah, I'm from Toronto, or just outside of Toronto, so it's always fun to come here. And yeah, I have to explain that. Yes, no, not that MDA, but the lesser known one. But and the scale of things here is wonderful, and you're doing some amazing work. So I appreciate you taking the time to have me up here and talk a little bit about what we've been doing. As Denny said, we've worked with the space program and folks down at JSC for a long time now. I thought usually when I give these presentations, I have the coolest pictures, but I'm kind of embarrassed now. Some of the ones this morning were lovely. But yeah, so one of our kind of first big products out of the Robotics and Automation group was the Canadarm you see here. And it's quite a sophisticated robotic system, and one of the nice things about it, it was able to handle the payloads inside the shuttle bay, be able to grab free flyers and move them around, and keep the operator in the relative safe confines of the shuttle. So it was a teleoperated robot that was able to allow the astronauts to move these big payloads around. From there, let's see, we go to Canadarm2. A little more of a sophisticated robot, but a very similar value proposition. This one's on the International Space Station, as many of you know. And again, teleoperated. This time had the capability you could operate it from the ground as well. So there's an added value of having ground crew be able to operate it and allow the astronauts to do other things. And this robot had some unique features. It has a shoulder and a hand that are interchangeable, so it can walk itself along the space station. It's 7 degrees of freedom, so it had a more sophisticated control structure and some more sophisticated sensing. Not to be outdone, we put an even more complicated robot up there called Dexter. This is a two-armed robot with a base, so it had 15 degrees of freedom in robot speak. And it had more sophisticated force sensing. So in this case, it was able to use those forces to adjust for sensed forces or contact when it was docking payloads into shelves. So it may have to accommodate binding forces and things like that. So it was becoming more sophisticated, using more data that it would sense on orbit, making the operator's job a lot easier. So what are these robotic systems doing? Why would you use these robotic systems? Well, a couple of real good values here is they take the human out of the dangerous environment, displace them a little bit from that environment. So in this case, space is a very harsh environment, and that's one of the big reasons you'd think about using a robot in this kind of situation. And then the other one, as I say, they're operating over a fairly, especially the first two robotics systems, Canadarm and Canadarm2, you're operating at a different scale. So the operator can sit there with his joysticks, and he's got his cameras and stuff like that, but he's able to actually manipulate payloads much easier and much larger than he would normally be able to do otherwise, he or she. So those are good robotic tasks. The other place we find robotics get used a lot of times is in the manufacturing environment. And in that case, it's often the case where you're trying to accelerate a process. So it could be an assembly line or a car or automotive plant where time is a factor, trying to improve your throughput. And the last one, last category I think about when looking for value propositions for robotic systems is using it as a platform to integrate information. And this is the one where I think medical robotics is finding a lot of value. So I was told to tell a story, so the story is going to tell us how some of the space robotics technology found its way into a medical application, a couple of medical applications. So this picture here just shows this is a car plant, shows I guess a more standard use of robotics up until, I guess, recently. Again, what you try to do there is to accelerate the timeline, and by doing that, or the way you do that is you structure the environment such that a robotic system understands where everything is, and it's able to act very quickly in a repetitive fashion. So that was always a good application for robotic systems. So it's improving the time value proposition. As I mentioned before, this robotic system and most of the ones that we work on don't operate at that kind of high speed, high transaction rate. But it is integrating, in this case, it's starting to integrate a lot more information to improve the astronaut's ability or user's ability to execute these tasks and in a harsh environment. So as we moved along that kind of continuum of our robotic systems becoming more and more sophisticated, I encountered this surgeon who's out of the University of Calgary, again in Canada, and he had at the time, it was a fairly unique operating room here. It has an intraoperative MRI. So that magnet there is on a set of overhead rails, and it's able to come in and out of a surgical theater. And this allows the neurosurgeon to be able to take MRI imaging just before a surgery, during a surgery, and then just after a surgery. And what I discovered, as I dealt with neurosurgeons, is they love their MRI imaging. And they want more and more to leverage that information at the time of surgery, not just in planning. So that was a whole theme behind this. And you can see there's some other elements in this surgical suite. Not only is there the most obvious one where the MRI comes in so you can take the pictures, but there's a tracking system that are now fairly ubiquitous in these surgical suites. There's a stereo camera pair that's a little bit off to the right there, hanging up on a post, and then there's a screen there that allows you to have a virtual overlay of your tool that's tracked by those cameras and position it relative to the patient's anatomy. So you can do navigation, non-invasive navigation. You can look inside the person's brain. You know what you're pointing at with your tool. So that's pretty cool. So Dr. Sutherland saw what we did on the International Space Station and came to us with this operational concept. His vision was using robotics. This is what he was trying to tell us with this picture, is to use robotics to link those images to the actual intervention, the actual positioning of those tools, so he could precisely position those tools based on that imaging. So we said, okay, that's interesting. I thought, well, at the time, We had been doing these teleoperated robotic systems for space. And we were also looking at Mars rovers, and we were looking at unique actuators, non-magnetic actuators. And we thought they'd be applicable to the MR environment, which is quite challenging. It's a big magnetic field, changing electrical fields. So some of that know-how of working in those harsh environments, we thought would be applicable to this project. So we said, of course we can do that. You just add those two things together, and you get exactly what... It turned out it was a little more difficult than that. It was quite a challenge, but what we ended up with is something called NeuroArm, derived from Canadarm, which is the Shuttle remote manipulator system. And what you can see here is a picture of Dr. Sutherland sitting at the workstation where he's got a very information-rich environment, and I think most people in mission control and in the space world would recognize that kind of workstation. And that is connected to a two-armed telerobotic system that could operate in and around the magnetic environment of the MRI, register to that MRI, and guide the tools in order to do precise neurosurgery. I've got a short video that will show you that the University of Calgary put together. It shows a little bit of the process of NeuroArm. So you can see here they're acquiring images before the surgery. They'll do their preoperative MRI. And then what you'll see is they'll bring in the robotic system, the microscope, and they'll connect it all together to do the surgery. So what happens up front, this is an open surgical procedure, so there's some preparation work that's not, a robotic system really doesn't add value to this part of the procedure. Where it's used is when more fine positioning is desired. So you can see our surgeons are operating under a magnified optical field, and what Dr. Sutherland was interested in is scaling the physical manipulation of the tools in the same way that he scaled his optical field, as well as registering the digital information of the MRI and bringing that all together in one platform. There's the upgraded workstation. There's a second iteration of that. It's quite interesting. In the course of this project, we started talking to Dr. Sutherland in 2002, and some technologies came a long way in that time, and the one that just sprung to mind was the 3D imaging capability. We had to end up building, at the time, a custom 3D display for him, and now that is dirt cheap off the shelf. It's amazing. And the post-operative engine. So that was Project NeuroArm. And the University of Calgary put together a poster. I was surprised one day flying into Calgary. I saw this at the airport. It was remarkable. It just reminds you why you do this. So that was the first patient that had the robotic system operate on her. Derived from space technology. So it was amazing. So there's one more story I want to tell, and then get back to some of the value proposition discussion. So. Are there any neurosurgeons here? Does anyone do neurosurgery or port-based neurosurgery? So port-based neurosurgery, it's a little bit like endoscopic surgery in that you place a port. In this case, you would use MRI imaging again to navigate a port to create a minimally invasive access corridor to a surgical location that you're trying to operate on. And what you can see in the image here is the surgeon has an exoscope camera looking down what would be the port, which is placed inside the patient's head, which is under the draping there. And in the screen there, you can see the round aperture there is the port that he's trying to look down. And the way it was traditionally done is that positioning arm was manually positioned. So a surgeon would release the arm, move it into place, align it as best they could with the port, and lock it back into place. And anytime they wanted to move that port around, they'd have to repeat that procedure. It was a little bit tedious. And it interrupted the workflow. And the company we started working with at the time was called Synaptive Medical. It was about 6 people at the time. And they had this idea that automating the position of that camera using a robotic system might be a good thing to do to improve this procedure. So what we did is we worked with them to very quickly, within about 3 months, we were able to put together a functioning demo, proof of concept of the system. And you can kind of see it there. We used a collaborative robotic system. Universal Robots is designed for industrial collaborative robotic applications. And we were able to bring some of the vision tracking system that we use for satellite servicing and layer it on top of that control system. And you can see, demonstrate the value of the system where they move the port around and it automatically, at the surgeon's command, would regain that nice view of the port so he could continue a surgical procedure. It turned out that was a highly desirable thing for that operation, and we created a system with Synaptive Medical called Bright Matter Drive. And I believe actually Houston Methodist Hospital here was an early adopter of that technology, so it's pretty exciting. Again, I show you a little video clip here of one of Aurora Medical Center was one of the first sites as well. And you can kind of see what they're doing here with this system is they're taking some very detailed MRI imaging. In this case, they've mapped out the fiber bundles inside the brain, and they're able to use that to plan a minimally invasive path for this port to be placed. This is all pre-planning, and then, as Dr. Kassam will say, he transfers that plan over to the system that's inside the surgical suite. So he's talking about there, and then he'll go inside the surgical suite and do the surgery. And what he's able to do is a few things. He's able to pre-plan certain positions for that camera, and he can be much more efficient at the time of the surgery because he's pre-planned how he wants the camera to move, what views he wants. He can return to certain views. And one thing that was interesting is situational awareness. So with this exoscope, it presents a two-dimensional image. And there was a lot of concerns with neurosurgeons. They're used to a surgical microscope that gives you a three-dimensional view. And so trying to keep the position, so that's what they're looking at when they're doing surgery. The relative position of things is sometimes difficult with the 2D view. And with the port, when you move around, you can kind of see the 3D structure as you kind of move your head around, even if you only have a 2D view, just by the relative position, the way things move. And having the robotic system that allows that to easily be done meant that he did it more often. So that was really fascinating. It was something we didn't really expect. He was doing 800 moves in a surgery. So just linking it back to the value propositions here. So time frame is not something that we've done in space or really derived, other than kind of maximizing astronaut time. But by that I really meant the rapid repetition of tasks. But the environment and operating at a scale, either a bigger scale or a smaller scale, and integrating information is really kind of where robotics can add value. And we talked a lot about robotics this morning, so keeping those in mind, I think, is useful. And I was really fascinated by the catheter robotic system this morning. It was really, robot worked beautifully. It was really good, and you can see it's delivering the value proposition of removing the radiologist from the radiation exposure, so that environment application or value proposition was really good. And scale, the control of the catheter was one that was really interesting, and something they commented on. One thing I thought was interesting, though, is, and it wasn't completely a fair demo with the camera here, but the situational awareness. So the integration of information, I think, is where there's a real opportunity for improvement in that kind of catheter-driving robotic application. So anyway, it was a really interesting demonstration. I thought it was really good. So that's all I have. Anyway, yeah. So thank you very much for listening.